Somewhere in the distant universe, more than 10 billion light years from Earth, there is a point of light so bright it outshines entire galaxies. But that light isn't coming from stars, it's coming from matter spiraling into something that, by all reasonable expectations, should not exist at the scale astronomers have measured it. A single black hole with a mass estimated at 66 billion times the mass of our Sun. Its event horizon alone could swallow our entire solar system many times over. Astronomers call it TON 618, and it is one of the most extreme objects ever discovered. Tonight, we're going to explore its true scale, and more importantly, we're going to confront a question that still troubles astrophysics. Why black holes this massive are so extraordinarily difficult to explain. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something that might surprise you. Black holes are not all the same. They come in vastly different sizes, and the difference between the smallest known black hole and the largest is so staggering that calling them by the same name almost feels misleading. Understanding those different scales is the first step toward grasping why TON 618 is so extreme and why it presents such a deep problem for astrophysics. So before we get to the monster itself, we need to build a ladder. We need to climb from the familiar to the unfamiliar, step by step, until we arrive at something that breaks the ladder entirely. The black holes most people have heard about, at least in passing, are stellar mass black holes. These are the remnants of massive stars. When a star significantly larger than our Sun, typically more than about 20 to 25 times more massive, reaches the end of its life, it runs out of nuclear fuel. For most of the star's existence, the outward pressure from nuclear fusion in its core has been holding it up, balancing the inward pull of gravity. Fusion is what keeps the star inflated, stable, shining. But when the fuel runs out, that balance collapses. Literally. The core of the star falls inward on itself in a fraction of a second. The outer layers, no longer supported, come crashing down and then rebound outward in a catastrophic explosion called a supernova. For a brief time, that explosion can outshine an entire galaxy. But while the outer layers are being blown into space, the core keeps collapsing. If enough mass remains in the core, no known force in nature can stop it. Not the electromagnetic force that holds atoms apart. Not the nuclear forces that hold atomic nuclei together. Not even the degeneracy pressure of neutrons packed as tightly as physics allows. Nothing is strong enough. The matter compresses past every threshold and forms a black hole. These stellar mass black holes typically range from about 5 to roughly 100 solar masses. A solar mass is simply the mass of our Sun, which is approximately 2 nonillion kilograms. A 2 followed by 30 zeros. That's already an incomprehensibly large number. And a stellar mass black hole contains 5 to 100 times that amount of material, crushed into a space far smaller than any planet. A black hole of 10 solar masses, for instance, would have an event horizon with a diameter of only about 60 kilometers. That's roughly the distance you might drive in half an hour on a highway. All the mass of 10 suns packed into a sphere smaller than a medium-sized city. The density implied by this is beyond anything in normal experience. These objects bend space-time so severely that time itself slows down in their vicinity. Light passing close to a stellar mass black hole gets dragged into curved paths that would be impossible under ordinary circumstances. Close enough, and even light gets pulled in and never escapes. That boundary, the point of no return, is what we call the event horizon. The first strong observational evidence for a stellar mass black hole came in 1971 with an object called Cygnus X1. This was a powerful source of X-rays in the constellation Cygnus, and astronomers determined that the X-rays were being produced by extremely hot gas spiraling into an invisible companion orbiting a massive blue star. The invisible companion was too heavy to be a neutron star. The only remaining explanation was a black hole. Since that discovery, astronomers have confirmed dozens of stellar mass black holes in our galaxy alone. And in recent years, gravitational wave detectors have revealed even more of them by catching the ripples in space-time produced when two black holes spiral into each other and merge. These detections have shown that stellar mass black holes can reach masses up to around 80 or 90 solar masses, especially through mergers. But even at the high end of that range, they remain in the same basic category. Objects born from stellar death, containing at most a few dozen to perhaps 100 times the mass of our Sun. Impressive as they are, stellar mass black holes are tiny compared to what lurks at the centers of galaxies. In the cores of most large galaxies, and likely all of them, sits a completely different class of object. A supermassive black hole. These are not formed from the collapse of a single star. They are millions to billions of times more massive than our Sun. And the gap between a stellar mass black hole and a supermassive one is not a gentle slope. It's a cliff. There's actually a mysterious gap in the middle, the so-called intermediate mass range between about 100 and 100,000 solar masses, where confirmed black holes are remarkably rare. We go almost directly from stellar mass objects to monsters millions of times heavier. That jump alone should tell you that supermassive black holes are something fundamentally different. The supermassive black hole we know best is the one at the center of our own Milky Way galaxy. It's called Sagittarius I star. This object has a mass of approximately 4 million times the mass of our Sun. 4 million solar masses. That's roughly 40,000 to 800,000 times more massive than a typical stellar mass black hole, depending on which stellar mass example you choose. And yet, by the standards of supermassive black holes, Sagittarius AY star is actually quite modest. It sits on the smaller end of the supermassive scale. We know Sagittarius I star exists because astronomers have spent decades painstakingly tracking the orbits of individual stars near the center of our galaxy. Using infrared telescopes that can peer through the gas and dust obscuring the galactic core, teams led by Andrea Ghez and Reinhard Genzel independently followed stars as they swung around an invisible point. One star in particular, known as S2, completes an orbit every roughly 16 years, reaching speeds of roughly 2.5% the speed of light at its closest approach. By watching these stars trace out their elliptical paths over years and decades, astronomers could calculate exactly how much mass must be concentrated at the center to produce that gravitational pull. The answer was about 4 million solar masses, all packed into a region smaller than our solar system. The only known object that could contain that much mass in that small a volume is a black hole. This work was so important that Gaze and Genzel were awarded the Nobel Prize in Physics in 2020. Despite its 4 million solar masses, Sagittarius A star is relatively quiet right now. It's not actively consuming large amounts of material. Occasionally, a wisp of gas drifts close enough to produce a faint flicker in X rays or infrared. But for the most part, the black hole at the heart of our galaxy sits in relative darkness, a massive but dormant engine. The fuel around it has largely been cleared away or settled into stable orbits that don't bring it close enough to fall in. Not all supermassive black holes are this calm. And this is where the story changes dramatically. Some supermassive black holes are surrounded by vast quantities of gas and dust. Material drawn in from the surrounding galaxy or supplied by collisions and mergers with other galaxies, or simply left over from the galaxy's formation. When that material spirals inward toward the black hole, drawn by its immense gravity, something spectacular happens. The gas doesn't fall straight in. Conservation of angular momentum forces it into a swirling disk. As it spirals closer and closer to the event horizon, the material gets compressed, and friction between layers of gas moving at different speeds generates extraordinary heat. Temperatures climb into the millions and even billions of degrees. At those temperatures, the gas radiates enormous amounts of energy across the entire electromagnetic spectrum: visible light, ultraviolet, X rays, radio waves, everything. The result is one of the most luminous phenomena in the entire universe. It's called a quasar. The word quasar needs careful explanation because it is one of the most misunderstood terms in astronomy. A quasar is not a type of star, despite the fact that the name originally came from quasi-stellar radio source, a label given in the early 1960s because these objects look like faint star-like points through a telescope. A quasar is not a galaxy, although every quasar lives at the center of one. And critically, a quasar is not the black hole itself. A quasar is the extremely bright, energetic core of a distant galaxy, powered by a supermassive black hole that is actively accreting, meaning actively consuming enormous amounts of surrounding material. The light you see when you observe a quasar does not come from inside the black hole. Nothing escapes from inside a black hole. The light comes from the material falling toward the black hole, specifically from the structure called the accretion disk. Think of it this way. Imagine a massive drain at the bottom of a lake. The drain itself is dark. You can't see anything inside it, but the water spiraling toward the drain moves faster and faster as it approaches. Now imagine that instead of water, it's superheated plasma, and instead of a gentle spiral, it's a violent maelstrom with material moving at a significant fraction of the speed of light. Friction and compression heat the gas to temperatures far beyond anything found on the surface of any star. And at those temperatures, the gas radiates staggering amounts of energy. That radiation, that light in all its forms, is what we detect as a quasar. This accretion disk, the swirling structure of infalling material, is the primary source of a quasar's luminosity. The black hole provides the gravity that makes the whole process possible, but the visible energy comes from the disk. This distinction matters enormously because when astronomers measure the brightness of a quasar, they are measuring the output of the accretion process, not the black hole directly. The black hole is inferred. It is deduced from the properties of the light, not observed on its own. And the brightness of a quasar can be truly extraordinary. A single quasar can outshine its entire host galaxy. Not by a small margin, but by factors of hundreds or even thousands. The host galaxy might contain hundreds of billions of stars, every one of them a nuclear furnace pouring out energy. And the quasar, a region perhaps no larger than our solar system at its core, produces more light than all of those hundreds of billions of stars combined. That is how powerful the accretion process becomes when a supermassive black hole is feeding at a high rate. The first quasar ever identified was 3C273, recognized as something extraordinary in 1963 by the astronomer Martin Schmidt. When Schmidt measured its redshift, a stretching of light caused by the expansion of the universe, he realized that this seemingly faint, star-like point was actually billions of light years away. For it to appear as bright as it did at such an enormous distance, it had to be producing an almost incomprehensible amount of energy. The only mechanism that could explain it was matter falling into a supermassive black hole. That discovery launched an entirely new field of astronomy. Now, here is where we need to be precise about terminology, because when we discuss an object like TON 618, there are several distinct components layered together, and they are not the same thing. First, there is the supermassive black hole itself. This is the central engine, the gravitational anchor. It has a specific mass, an event horizon of a specific size, and it sits at the very center of the system. You cannot see it directly. No light escapes from it. Second, there is the accretion disk. This is the swirling structure of superheated gas that orbits the black hole, gradually spiraling inward. The inner edge, closest to the event horizon, is the hottest and brightest. This disk is the primary source of luminosity. Third, there is the host galaxy. The black hole and its accretion disk exist at the center of an entire galaxy with its own stars, gas, and dust. In many cases, the host galaxy of a quasar is incredibly difficult to observe because the quasar is so overwhelmingly bright that it drowns out the surrounding starlight. It's like trying to see a firefly perched on the face of a searchlight. And fourth, there is the quasar itself. The quasar is not a separate physical object, it's the phenomenon. It's the combined observational signature of all that accretion, the enormous luminosity, the specific spectral features, the variability. When we say we observe a quasar, we mean we see the effects of a supermassive black hole actively feeding. The quasar is what we detect. The black hole is what we infer from what we detect. This brings us to TON 618. The story begins in 1957 at a small observatory in central Mexico. The Tonantzintla Observatory, located in the state of Puebla, was conducting a photographic survey of the sky, cataloging objects by their brightness and color. Among the many objects logged was an unremarkable looking point of light, blue in color, assigned the catalog number TON 618. TON simply stood for the name of the observatory. At the time, nobody knew what this object truly was. It looked like a faint bluish star. Nothing about it screamed that it was special. It was one entry among many on a photographic plate, filed away and largely forgotten. It took years before anyone realized what TON 618 actually was. In the decades following the identification of 3C273 as a quasar, astronomers began systematically revisiting catalogs of blue stellar objects, hunting for more quasars hiding in the data. Blue color was a telltale clue because the intense radiation from a quasar's accretion disk tends to make it appear blue compared to ordinary stars. TON 618 eventually drew attention because its spectrum, the detailed fingerprint of its light showed features that didn't match any normal star or nearby galaxy. If you wanted to find Ton 618 in the night sky, you would look toward the constellation Konis Vaenat Isi, the hunting dogs. It's a small, relatively faint constellation in the northern sky, tucked below the handle of the Big Dipper. There's nothing dramatic about the patch of sky where Ton 618 resides. No bright stars nearby to guide your eye. No nebulae or obvious clusters. Just an ordinary field of faint stars. And among those faint points, if you had a moderately large telescope, you would see Ton 618 as one more unremarkable dot. A dim smudge of light, barely distinguishable from the thousands of faint stars surrounding it. You would have no reason to look twice. Nothing about its appearance through a telescope hints at what it truly is. That's the staggering thing. One of the most extreme objects in the observable universe looks like absolutely nothing special through an eyepiece. It took spectroscopy, the careful analysis of its light broken into component wavelengths, to reveal that this faint dot was not a star in our galaxy, but something vastly more distant, vastly more luminous, and vastly more powerful than almost anything else in the cosmos. When astronomers measured the redshift of Ton 618, the result was extraordinary. The redshift was approximately 2.22. In cosmology, redshift tells you how much the light from a distant object has been stretched by the expansion of the universe during its long journey to your telescope. The higher the redshift, the farther away the object is, and the further back in time you're looking. A redshift of 2.22 corresponds to a look-back time of roughly 10.8 billion years. Let that number settle for a moment. When we observe Ton 618, we are seeing light that left its source approximately 10.8 billion years ago. The universe itself is only about 13.8 billion years old. That means we're looking at Ton 618 as it existed when the universe was roughly 3 billion years old. We're seeing it in cosmic youth. The universe was less than a quarter of its current age. Galaxies were still assembling, stars were forming at furious rates. The cosmos was denser, hotter, more chaotic, and younger than anything we see in our local neighborhood today. And this is not a coincidence. Quasars were not distributed evenly across cosmic history. They were far more common in the early universe than they are today. The peak of quasar activity occurred roughly 10 to 12 billion years ago, precisely the era we are observing when we look at Ton 618. During that epoch, galaxies were colliding more frequently because the universe was smaller and denser. Those collisions funneled enormous quantities of gas toward the central black holes, feeding them at prodigious rates and lighting up the quasar phenomenon across the cosmos. Today, in the modern universe, quasars are relatively rare. Most supermassive black holes have settled into quiet dormancy. Their fuel supplies long since consumed or dispersed. When we observe Ton 618, we are not looking at a freak event in the modern cosmos. We are looking at a product of a specific cosmic era, a time when the universe was optimally configured to build the most extreme engines of accretion it would ever produce. Ton 618 belongs to that era. It is a relic of the universe's most active and violent youth, seen across 10 billion light years of intervening space. And what we see at that distance is astonishing. Ton 618, despite being more than 10 billion light years away, is still extraordinarily bright. Its luminosity has been estimated at roughly 140 trillion times the luminosity of our sun. 140 trillion suns. Our sun provides all the light and heat for our entire planet. It powers every ecosystem, every weather system, every living thing on Earth. And TON 618's accretion disk produces the equivalent energy output of 140 trillion stars like ours, simultaneously from a region that, at its core, may be no larger than our solar system. That luminosity does not come from stars. It comes from the accretion disk, from superheated material spiraling into the central black hole. And for the disk to produce that much energy, the black hole powering it must be extraordinarily massive. This is the key chain of reasoning. The brightness of the quasar constrains the properties of the accretion disk. The accretion disk constrains the mass of the black hole. Astronomers work backward from what they can see to what they cannot. And when they performed that calculation for TON 618, the result was staggering. The supermassive black hole at its center has an estimated mass of roughly 66 billion times the mass of our sun. 66 billion solar masses. Let's try to understand what that number actually means. Sagittarius IY star, the supermassive black hole at the center of our own galaxy, has a mass of about 4 million solar masses. That already dwarfs any individual star ever observed. The most massive stars known are perhaps 200 to 300 solar masses. Sagittarius E star contains the equivalent of more than 10,000 of those most massive stars, all compressed into a single gravitational object. It's already a fundamentally different category of thing. But TON 618 makes Sagittarius I star look insignificant. 66 billion solar masses is approximately 16,500 times more massive than the black hole at the center of our galaxy. If Sagittarius I star were the mass of a single marble, the black hole in TON 618 would outweigh a large car. The two objects share the same name, supermassive black hole, but the scale separating them is almost absurd. Here is another comparison that might help. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Most of those are small red dwarfs with masses well below our sun's. The total stellar mass of the Milky Way, every star added together, is estimated at roughly 40 to 60 billion solar masses. That means the black hole at the center of TON 618 has a mass comparable to, and possibly exceeding, the combined mass of every single star in our entire galaxy. One black hole, rivaling the total stellar mass of hundreds of billions of suns. Let's try one more angle to make this concrete. Our entire solar system, the sun plus all 8 planets, all their moons, the asteroid belt, the Kuiper belt, every comet and grain of dust, has a combined mass of roughly 1.0014 solar masses. The sun dominates so completely that everything else is a rounding error. To assemble the mass of TON 618's black hole, you would need roughly 66 billion copies of our solar system. 66 billion complete solar systems, each with its own star, its own planets, its own moons, all of them dismantled and compressed into a single gravitational point. If you could somehow line up those 66 billion solar systems and feed them one by one into the black hole, adding a new solar system every single second, it would take you more than 2,000 years to finish. Day and night, second after second, for longer than the time separating us from the Roman Empire, just to deliver enough mass. That comparison deserves a pause because it inverts everything we intuitively assume about how the universe is organized. In our experience, galaxies are the big structures. They contain hundreds of billions of stars spread across tens of thousands of light years. The black hole at the center is a comparatively small, concentrated point. In the Milky Way, Sagittarius II star represents only about 1/10 of 1% of the galaxy's total mass. It matters. It influences the stars near it, but it's a tiny fraction of the whole. Ton 618 shatters that proportion. Here is a black hole so massive that it rivals the total stellar content of a galaxy like our own. The relationship between the central engine and its surroundings is something qualitatively different from what we observe in our cosmic neighborhood. And that immediately raises the most important question. How did this happen? How did this black hole accumulate 66 billion solar masses? And how did it do so within the first 3 billion years of cosmic history? When the universe was still young, still assembling its first generations of galaxies? These are not idle questions. They lead directly into some of the most challenging and fascinating problems in modern astrophysics. Because there are physical limits on how quickly a black hole can grow, limits set by the very process that makes quasars luminous. And those limits make it extremely difficult, perhaps seemingly impossible at first glance, to construct a black hole as massive as the one in Ton 618 in the time that was available. But before we confront that problem, we need to do something else first. We need to truly understand the physical scale of this object. Not just the mass as a number, but what that mass implies about the size of the event horizon, the reach of its gravity, and how it compares to structures we're familiar with, like the orbits of the planets in our own solar system. Because the mass alone, as staggering as it is, only tells part of the story. When you translate 66 billion solar masses into physical dimensions, into a size you can compare against the distances between worlds, the result is something that pushes against the boundaries of what you thought a single object in the universe could be. We've established the number 66 billion solar masses, but a number that size has a way of sliding off the mind without leaving a mark. You hear it, maybe you nod, and then it fades because your brain simply has no framework for holding something that extreme. So, what we need to do now is translate that mass into physical dimensions, into sizes and distances and comparisons that make the enormity real. Because when you truly grasp what 66 billion solar masses means in terms of physical space, when you see what the event horizon of this black hole would look like placed next to familiar objects, something shifts in your understanding of the universe. You realize that Ton 618 is not just a very large black hole. It is an object that redefines what you thought a single thing in the universe could be. Let's start with the event horizon. The event horizon of a black hole is the boundary beyond which nothing can escape. Not light, not matter, not information of any kind. Anything that crosses the event horizon is lost to the outside universe forever. It doesn't matter how fast you're moving, how powerful your engines are, or how much energy you have. Once you cross that line, the geometry of space-time itself curves inward so steeply that every possible path, even the paths light takes, leads deeper into the black hole. There is no outward direction anymore. The event horizon isn't a physical surface. It's not a wall or a shell. You wouldn't feel anything special as you crossed it. At least not for a black hole this large. But once you're past it, there is no going back. The event horizon is not a place you visit. It is a threshold you cross exactly once. The size of the event horizon depends directly on the mass of the black hole. More mass means stronger gravity, which means space-time is curved over a larger region, which means the event horizon extends farther out. The relationship is described by something called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who worked out the mathematics in 1916, barely a year after Einstein published his general theory of relativity. The Schwarzschild radius gives you the radius of the event horizon for a non-rotating black hole, and the formula is elegant in its simplicity. The radius scales linearly with mass. Double the mass, you double the radius. Triple the mass, triple the radius. 10 times the mass, 10 times the radius. For our sun, if you could somehow compress its entire mass into a black hole, the Schwarzschild radius would be about 3 kilometers. 3 kilometers. All the mass of the sun compressed into a sphere you could walk across in about half an hour. For a stellar mass black hole of 10 solar masses, the radius is about 30 kilometers. For Sagittarius I star, with its 4 million solar masses, the Schwarzschild radius is about 12 million kilometers. That sounds enormous, and in absolute terms it is, but let's put it in context. The distance from the Sun to Mercury, the innermost planet in our solar system, is about 58 million kilometers. Sagittarius A star's event horizon would fit comfortably inside Mercury's orbit. The black hole at the center of our galaxy, massive as it is, has an event horizon that is small compared to the scale of a planetary system. Its radius is roughly 17 times the radius of the Sun. Significant? Yes, but compact by solar system standards. Now let's calculate what happens with 66 billion solar masses. The Schwarzschild radius scales linearly, so we multiply. 3 kilometers per solar mass times 66 billion. That gives approximately 198 billion kilometers. 198 billion kilometers. And that is just the radius. The full diameter from one side of the event horizon to the other is roughly 396 billion kilometers. Those numbers are too large to mean anything on their own. So let's convert them into a unit that helps. Astronomers measure distances within solar systems using astronomical units. One astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. Divide 198 billion by 150 million, and you get approximately 1,300 astronomical units for the radius. The full diameter of the event horizon is about 2,600 astronomical units. Now, let's place that against our solar system. Earth orbits the Sun at 1 astronomical unit. Mars orbits at about 1.5. Jupiter sits at roughly 5. Saturn about 9.5. Uranus about 19. Neptune, the outermost planet, about 30. Pluto, the dwarf planet, orbits at an average of roughly 40 astronomical units. The event horizon of the black hole in TON 618 has a radius of approximately 1,300 astronomical units. Not a diameter. A radius. If you place this black hole where our Sun is, its event horizon would extend outward 1,300 times the distance from Earth to the Sun. Every planet in the solar system would be deep inside the event horizon. Not near the edge, not close to the boundary. Deep inside. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, all buried within it. Hundreds of astronomical units from the nearest boundary in every direction. And the event horizon doesn't stop at Pluto. It keeps going. Far past the Kuiper Belt. Far past the scattered disk of icy bodies populating the outer solar system. The Voyager 1 spacecraft, launched in 1977, has been traveling away from Earth for nearly 50 years. As of 2025, it is roughly 165 astronomical units from the Sun. It is the most distant human-made object in existence. It has crossed the heliopause, the boundary where the solar wind gives way to interstellar space. And the event horizon of TON 618 would extend nearly 8 times farther out than Voyager 1 has traveled in half a century. At its current speed, Voyager would need roughly another 3.5 centuries of travel just to reach the edge of this black hole's event horizon. The heliopause, which many scientists consider the functional boundary of our sun's direct influence, sits at roughly 120 astronomical units. The event horizon of TON 618 extends to 1,300 astronomical units. That means this single object's event horizon is more than 10 times the radius of the heliosphere. The entire domain where the solar wind blows, the entire region of space our sun controls, could fit inside TON 618's event horizon more than 10 times over along the radius alone. Let me give you one more comparison that makes the scale visceral. If you could travel at the speed of light, 300,000 kilometers per second, and you wanted to cross the full diameter of TON 618's event horizon from one side to the other, it would take you roughly 15 days. 15 days. Traveling at the fastest speed anything in the universe can possibly move, just to cross the diameter of one object. For comparison, light crosses the distance from the Earth to the Sun in about 8 minutes and 20 seconds. Light crosses the distance from the Sun to Neptune in about 4 hours. Light crosses the event horizon of TON 618 in about 15 days. That is the scale of this thing. Now, let's compare it to other black holes that are already famous for being enormous. Sagittarius IE star has a Schwarzschild radius of roughly 0.08 astronomical units, smaller than a tenth of the Earth-Sun distance. M87's black hole, the supermassive object at the center of the giant elliptical galaxy in the Virgo cluster, has a mass of about 6.5 billion solar masses. This is the black hole that was directly imaged in 2019 by the Event Horizon Telescope collaboration. The one that produced that iconic photograph of a glowing orange ring surrounding a dark central shadow. That black hole has a Schwarzschild radius of approximately 130 astronomical units. Its full diameter is about 260 astronomical units. That means M87's event horizon would extend well past Pluto's orbit. It would engulf the entire classical solar system, every planet swallowed. And TON 618 is roughly 10 times more massive than M87's black hole. Its event horizon has roughly 10 times the radius. 130 astronomical units for M87 versus 1,300 for TON 618. If M87's black hole would engulf the solar system out to roughly 3 times the orbit of Pluto, TON 618 would engulf the solar system and keep reaching outward for more than 1,000 additional astronomical units in every direction. M87's black hole was already considered extraordinary when it was imaged. It was hailed as one of the most massive black holes known. TON 618 dwarfs it by an order of magnitude. Given the sheer size of this event horizon, you might assume that approaching it would be one of the most violent experiences imaginable. You might picture something dramatic. The immense gravity ripping apart anything that comes close, stretching and tearing matter into threads of plasma long before it reaches the boundary. And for small black holes, That picture is exactly right. When you approach a stellar mass black hole, one with perhaps 10 or 20 solar masses, the tidal forces become extreme. Tidal forces arise because gravity is stronger on the side of your body closer to the black hole than on the side farther away. That difference in gravitational pull stretches you lengthwise and compresses you sideways. Physicists call this spaghettification, and the name is disturbingly accurate. You would be drawn into a long, thin strand of matter well before reaching the event horizon. For a small black hole, the tidal forces at the event horizon are savage. But here is one of the most counterintuitive facts about TON 618. The bigger the black hole, the gentler the tidal forces at the event horizon. This sounds backward, but it follows directly from the physics. A more massive black hole has a larger event horizon, which means the boundary is farther from the central point where gravity is technically infinite. At the event horizon of a stellar mass black hole, you are very close to the center, and the gradient in gravity across your body is enormous. At the event horizon of TON 618, you are 1,300 astronomical units from the center. Gravity is still powerful enough that nothing can escape. But the difference in gravitational pull between your head and your feet is negligible. You could cross the event horizon of TON 618 and feel nothing unusual at all. No stretching, no compression, no warning. You would pass from the outside universe into the interior of the black hole without any perceptible change. The only way you would know you had crossed would be that you could never return. Every direction you could possibly travel would lead deeper in. That is what 66 billion solar masses buys you. An event horizon so vast that its curvature at the boundary is gentle enough to be unnoticeable by a human body. Of course, the calm doesn't last. Once inside, you're falling toward the singularity, the point at the center where our physics breaks down entirely. The tidal forces that were negligible at the event horizon grow steadily stronger as you fall deeper. Eventually, the stretching becomes extreme. But for TON 618, that process takes time. The total fall from the event horizon to the singularity would last roughly 12 days of your own personal time. For most of that fall, days on end, you would feel nothing unusual at all. Only in the final stretch, as you plunge close to the center, would tidal forces begin to build and eventually become destructive. Compare that to a stellar mass black hole, where spaghettification begins before you even reach the event horizon, and the entire process takes fractions of a second. But the event horizon, vast as it is, represents only part of the picture. A black hole does not sit passively in space, affecting nothing beyond its boundary. Gravity extends far past the event horizon. It weakens with distance, following the inverse square law, but it never reaches zero. And for a black hole this massive, the gravitational influence extends across enormous volumes of space. Astrophysicists use a concept called the gravitational sphere of influence. This is the region surrounding a black hole within which the black hole's gravity dominates over the collective gravity of surrounding stars in the host galaxy. Outside this sphere, the combined gravitational pull of billions of stars matters more than the black hole does. Inside it, the black hole is king. Everything, stars, gas, dust, orbits according to the black hole's commands. For Sagittarius A star, the gravitational sphere of influence extends roughly 6 to 10 light years from the galactic center. Within that zone, individual stars orbit the black hole rather than the general gravitational field of the galaxy. Beyond that, The Milky Way's overall mass distribution takes over. Our Sun, sitting 26,000 light years out, barely feels Sagittarius I star's direct pull. For a black hole with 66 billion solar masses, the sphere of influence is predicted to be vastly larger. The precise size depends on properties of the host galaxy that are extremely difficult to measure because the quasar's light drowns out everything around it. But reasonable estimates suggest that TON 618's black hole gravitationally dominates a region extending several thousand light years from the center. Several thousand light years. To put that in perspective, if you drew a sphere several thousand light years in radius around the center of our galaxy, it would contain millions of stars. And for all of those stars, their orbits would be dictated primarily by one object, not the collective mass of 100 billion neighbors, just one single gravitational anchor. That is the kind of dominance this black hole exerts over its environment. Now let's talk about what surrounds the black hole, because the event horizon itself is invisible. What makes TON 618 detectable across 10 billion light years of space is the colossal structure of superheated material encircling it, the accretion disk. The accretion disk of a quasar like TON 618 is not a simple uniform ring. It has structure, it has layers, it has temperature gradients that span an extraordinary range. At the outermost edges, where material is still orbiting at relatively modest speeds and has not yet been compressed significantly, temperatures might be in the tens of thousands of degrees, hot enough to glow brightly, but comparable to the surfaces of hot stars. Moving inward, toward the black hole, the picture changes drastically. The material spirals faster and faster. Friction between adjacent layers of gas moving at different speeds generates tremendous heat. Compression adds more. By the time you reach the inner edge of the disk, closest to the event horizon, temperatures climb into the hundred of millions or even billions of degrees. This inner region radiates primarily in X-rays and extreme ultraviolet, wavelengths of light that carry enormous energy. The physical size of the accretion disk extends well beyond the event horizon. The innermost stable circular orbit, the closest distance at which material can orbit without spiraling directly in, sits at a few times the Schwarzschild radius for a non-spinning black hole. For TON 618, that means the inner edge of the disk might be a few thousand astronomical units from the center. But the disk extends outward much further than that. Accretion disks around supermassive black holes in luminous quasars can extend outward for thousands or tens of thousands of astronomical units. The full structure from inner rim to outer edge could span a significant fraction of a light year. An object far larger than any star, far larger than any stellar system, yet still tiny compared to the galaxy it inhabits. If you could somehow observe this accretion disk from nearby, the view would be profoundly strange. General relativity warps the appearance of everything near a massive black hole. Light from the far side of the disk, the part behind the black hole relative to your line of sight, doesn't simply disappear. Instead, the black hole's gravity bends that light around itself, curving photon paths so severely that you can see parts of the disk that should geometrically be hidden behind the black hole. The result is a visual distortion that makes the disk appear to wrap around the black hole. You would see a bright ring of light surrounding a dark central shadow, with the disk appearing to arch up and over the top and curve down beneath the bottom simultaneously. The iconic image of M87's black hole captured in 2019 shows exactly this effect. A glowing ring with a dark center. For TON 618, the same physics applies, but at a scale roughly 10 times larger. The ring of fire would be 10 times wider. Many quasars, potentially including TON 618, also launch relativistic jets. These are narrow beams of material accelerated to speeds approaching the speed of light, shot outward from the poles of the accretion disk, perpendicular to the plane of the disk itself. The precise mechanism that creates these jets is still debated, but it likely involves magnetic fields twisted and amplified by the spinning accretion disk, and possibly the spin of the black hole itself. These magnetic fields can channel material into tight beams and accelerate it to extraordinary velocities. When these jets are present, they can extend far beyond the galaxy. Some quasar jets have been observed stretching hundreds of thousands of light years into intergalactic space. They carry enormous energy, plowing through surrounding gas, heating it, pushing it aside, and inflating vast cavities in the intergalactic medium. These jets represent one of the ways a black hole's influence can reach far beyond its gravitational sphere of influence, affecting the evolution of not just its own galaxy, but the broader cosmic environment around it. Below all of this spectacle, buried beneath the quasar's overwhelming glare, is the host galaxy. We know it must be there. Every supermassive black hole inhabits the center of a galaxy, but for TON 618, the host galaxy is extraordinarily difficult to observe. The quasar is so bright that it drowns out the starlight of the surrounding galaxy the way a searchlight drowns out a candle placed next to it. Attempts to detect the host galaxy have produced only marginal results. Some studies suggest the presence of a massive galaxy, which makes sense because the most massive black holes tend to reside in the most massive galaxies. But the details remain elusive. We can say with confidence that a galaxy is there, hosting the black hole and feeding it. But its properties, its size, its stellar population, its structure, all of these remain poorly constrained, hidden behind the blinding light of the quasar. Now let's talk about luminosity. The mass and size of the event horizon describe the black hole itself, but the luminosity describes the spectacle it creates around it. And the spectacle is extraordinary. The light from TON 618 comes from its accretion disk, the vast structure of superheated material spiraling inward toward the event horizon. This disk is the most efficient energy generating mechanism known to physics. When matter falls toward a black hole, it loses gravitational potential energy. That energy gets converted into kinetic energy, then into thermal energy through friction and compression, and finally into electromagnetic radiation, light in all its forms. This process can convert roughly 10% of the rest mass energy of infalling material into radiation. That might not sound impressive until you compare it to nuclear fusion, the process that powers every star in the universe. Fusion converts less than 1% of the rest mass of hydrogen into energy. Accretion onto a black hole is more than 10 times more efficient than the nuclear furnaces inside stars. A black hole's accretion disk extracts more energy per unit of mass than any star could ever produce. The luminosity of TON 618 has been estimated at approximately 140 trillion times the luminosity of our Sun. Let's try to unpack that. Our Sun produces roughly 3.8 times 10 to the 26th watts of power. That's already an enormous number. It keeps every ecosystem on Earth running. It drives every weather system. It sustains every living thing on Earth. And Ton 618's accretion disk produces 140 trillion times that amount of energy. Now consider this. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. But most of those stars are dim red dwarfs contributing very little light. The total combined luminosity of every star in the Milky Way, from the faintest embers to the brightest blue giants, is estimated at roughly 10 to 30 billion solar luminosities. Ton 618's accretion disk produces 140 trillion solar luminosities. That is roughly 5,000 to 14,000 times the total light output of our entire galaxy. One accretion disk, powered by one black hole, outshining the Milky Way by a factor of thousands. If you gathered several thousand galaxies identical to the Milky Way and added up all their starlight, you would only then approach the energy output of this single quasar. If Ton 618 were placed at the center of our galaxy, the radiation would transform everything. The light from its accretion disk would be visible during the day, brighter than the sun in our sky. X-rays and ultraviolet radiation would bathe the inner galaxy at intensities that would strip atmospheres from planets and sterilize surfaces across thousands of light years. Life in the inner half of the galaxy would be impossible. One accreting black hole would reshape the conditions for existence across an entire galactic disk. And yet even this staggering luminosity has a ceiling. There is a theoretical maximum brightness for an accreting object, called the Eddington luminosity. This limit exists because of a fundamental tug of war. As material falls inward, it releases radiation. That radiation pushes outward on the infalling material, exerting pressure. The more material falls in, the more radiation is produced, and the stronger the outward push becomes. At some point, the outward radiation pressure exactly balances the inward gravitational pull, and no additional material can fall in. The luminosity at that balance point is the Eddington limit. Crucially, it depends directly on the mass of the black hole. A more massive black hole has stronger gravity, so it can hold onto infalling material against stronger radiation pressure, which means it can sustain a higher luminosity before the balance tips. For Ton 618, with its 66 billion solar masses, the Eddington luminosity is extraordinarily high, and the observed luminosity of the quasar appears roughly consistent with, or perhaps somewhat below, this theoretical maximum. This tells astronomers something important. The accretion disk is feeding the black hole at or near the maximum possible rate. The engine is running close to full throttle. And the fact that the observed luminosity aligns with the Eddington limit for a black hole of this mass provides an independent check on the mass estimate. If the black hole were much less massive, it could not sustain this luminosity without blowing away all its fuel. The brightness itself, through the Eddington relationship, constrains how massive the black hole must be. This is one of the central tools astronomers use to estimate black hole masses in distant quasars. We cannot see Ton 618's black hole directly. We cannot watch stars orbiting it the way we track stars around Sagittarius I star. It is far too distant for that. What we can measure is the light. And from that light, using the physics of accretion and the relationship between luminosity and mass, we can work backward to infer the mass of the engine powering it. But that inference is not simple. It involves assumptions about how the accretion disk is oriented, how efficiently it converts mass into radiation, whether the black hole is spinning and how fast, and whether the quasar's light has been amplified or obscured by anything along the line of sight. Each of these factors introduces uncertainty. The mass of 66 billion solar masses is an estimate, the best fit to the available data. The true mass could be somewhat higher or somewhat lower, but even allowing for reasonable uncertainty, you're still dealing with an object of tens of billions of solar masses. The fundamental conclusion that this is one of the most massive black holes ever measured holds firm. So here is where we stand. TON 618 is a quasar, the brilliant signature of an actively feeding supermassive black hole at the center of a distant galaxy. The black hole has an estimated mass of 66 billion solar masses. Its event horizon spans a diameter of roughly 2,600 astronomical units, large enough to engulf our entire solar system many times over and reach deep into interstellar space. Its accretion disk, a vast structure of superheated gas stretching potentially thousands of astronomical units beyond the event horizon, radiates at temperatures from tens of thousands to billions of degrees, producing roughly 140 trillion solar luminosities and outshining the entire Milky Way by a factor of thousands. Its gravitational influence extends across thousands of light years, dominating the dynamics of everything near the galactic core. And despite all this violence and power, the event horizon itself is so vast that crossing it would feel like nothing at all. This object is not just big. It occupies a completely different category of existence compared to the black holes in our own galaxy. Sagittarius I star fits inside the orbit of Mercury. TON 618 swallows the entire solar system and keeps reaching. Sagittarius I star sits quietly, barely nibbling on wisps of gas. TON 618 radiates brighter than entire galaxies. The difference is not one of degree, it is one of kind, like comparing a campfire to the detonation of a star. And all of this raises an essential question. How do we actually know any of this? How can astronomers, sitting on a small rocky planet, observing a point of light more than 10 billion light years away, determine the mass of a black hole they will never see, inside a galaxy they can barely detect, at a distance so vast that the light left its source when the universe was still assembling its first structures? The answer involves some of the most powerful and elegant techniques in modern astronomy. And understanding those methods matters because without them, the numbers we've discussed tonight, 66 billion, 1,300 astronomical units, 140 trillion, are just claims. With them, they become measurements. Inferred, yes. Indirect, yes. But measurements grounded in physics, tested against observations, and refined across decades of careful work. We've now walked through what TON 618 is, what the quasar phenomenon represents, and what the estimated mass of its central black hole implies in physical terms. 66 billion solar masses, an event horizon spanning 2,600 astronomical units, a luminosity that outshines the Milky Way thousands of times over. These numbers are staggering, and they naturally provoke a question that deserves a careful, honest answer. How do astronomers actually arrive at numbers like these? How do you weigh something you cannot see, inside a galaxy you can barely detect, more than 10 billion light years away? Because the answer to that question determines how much trust you should place in the numbers themselves. And the honest answer is that these are not direct measurements. They are inferences. Powerful inferences grounded in well-tested physics, but inferences nonetheless. And they carry real uncertainties that matter. Let's start with the basic problem. When astronomers observe TON 618, through a telescope, they do not see a black hole. They see light. A point of light that, even with the most powerful instruments, remains unresolved, meaning it appears as a dot rather than a disk or a structure with visible features. All the information we have about the black hole must be extracted from that light, specifically from the spectrum of that light, the way the light is distributed across different wavelengths. When you pass light through a prism or a spectrograph, it spreads out into a rainbow of colors. Each wavelength corresponds to a specific energy of light, and embedded in that rainbow are patterns, bright lines where certain wavelengths are unusually intense, dark lines where certain wavelengths are absorbed. These spectral lines are fingerprints. Every element and every ion in the universe emits and absorbs light at specific known wavelengths. Hydrogen produces a particular set of lines. Helium produces a different set. Carbon, oxygen, magnesium, iron, each has its own characteristic pattern. By examining which lines appear in the spectrum of a distant object, astronomers can determine what that object is made of and, crucially, how that material is moving. This is where the Doppler effect enters the story. When a light source is moving toward you, its wavelengths are compressed. The light shifts toward shorter wavelengths, toward the blue end of the spectrum. When a light source is moving away from you, its wavelengths are stretched. The light shifts toward longer wavelengths, toward the red end. If the source is moving very fast, the shift is large. If it's moving slowly, the shift is small. By measuring how much a spectral line has shifted from its known rest wavelength, you can determine how fast the source is moving along your line of sight. Now, here is the critical insight. When astronomers look at the spectrum of a quasar like TON 618, they see emission lines. These are bright spectral lines produced by gas that is being energized by the intense radiation from the accretion disk. The gas is being heated and ionized, stripped of its electrons, and when those electrons recombine with atoms or the atoms transition between energy states, they emit light at specific wavelengths. But these emission lines are not sharp, narrow peaks. They are broad, very broad. Instead of a thin spike at a precise wavelength, the lines are smeared out across a wide range of wavelengths. And this broadening is the key to everything. Why are the lines broad? Because the gas producing them is not sitting still. It is orbiting the black hole at tremendous speed. Some of that gas is moving toward us as it swings around one side of its orbit. That gas produces light that is blue shifted toward shorter wavelengths. Other gas is moving away from us on the other side of its orbit, producing red shifted light. Still, other gas is moving sideways relative to our line of sight, contributing light near the central wavelength. The combined effect of all this gas, moving at different speeds in different directions, is that the emission line gets smeared out, broadened. The faster the gas is moving, the broader the line becomes. Astronomers call the region where this fast-moving gas resides the broad line region. This is a zone relatively close to the black hole, probably within a few light weeks to a few light months of the central engine, where dense clouds of gas orbit at thousands of kilometers per second. The broad line region is far enough from the black hole that the gas isn't falling in, at least not immediately. It's orbiting, but it's close enough that the orbital velocities are enormous, driven by the immense gravitational pull of the black hole. And this is where the mass estimate comes from. The principle is straightforward, even if the details are complex. If you know how fast the gas is moving, and you know how far it is from the black hole, You can calculate the mass of the black hole using the same gravitational physics that lets you calculate the mass of the sun from the speed and distance of Earth's orbit. The mass equals the velocity squared times the distance, divided by the gravitational constant. It's the same equation Newton would have recognized, applied to gas orbiting a black hole billions of light years away. The velocity part comes from the width of the broad emission lines. Astronomers measure what's called the full width at half maximum of the line. This is essentially a measure of how broad the line is, which directly encodes the range of velocities in the gas. Wider lines mean faster gas. For TON 618, the broad emission lines indicate gas velocities of several thousand kilometers per second. This is extraordinarily fast. For comparison, Earth orbits the Sun at about 30 kilometers per second. The gas in the broad line region of TON 618 is moving hundreds of times faster. The distance part is harder. You can't directly see how far the broad line region is from the black hole. TON 618 is too far away and too compact to resolve spatially. But astronomers have a clever technique called reverberation mapping that can measure this distance indirectly. The idea behind reverberation mapping is elegant. The accretion disk, the primary source of the quasar's continuum radiation, is not perfectly steady. It flickers. Its brightness varies on timescales of days to weeks, driven by instabilities and fluctuations in the rate at which material falls inward. When the accretion disk brightens, the increased radiation travels outward at the speed of light and eventually hits the gas in the broad line region. The gas responds, it gets more energized, and the emission lines brighten too. But there is a delay. The accretion disk brightens first, then, after a measurable time lag, the emission lines brighten. The duration of that lag tells you how far the broad line region is from the central source. If the lag is 10 days, the broad line region is roughly 10 light days away. If it's 30 days, roughly 30 light days. The light travel time directly encodes the physical distance. By combining the velocity from the line width with the distance from the reverberation lag, astronomers can calculate the mass. This method is called the virial method because it's based on the virial theorem, a fundamental principle in physics that relates the kinetic energy of a gravitationally bound system to the gravitational potential energy holding it together. Reverberation mapping has been applied directly to dozens of quasars and active galaxies. It works. It produces mass estimates that are consistent with other methods where those other methods can be checked. For nearby galaxies where we can measure black hole masses by tracking the orbits of individual stars near the center, the reverberation mapped masses agree reasonably well with the star orbit masses. This gives astronomers confidence that the virial method produces reliable results, at least to within a factor of a few. However, reverberation mapping requires monitoring a quasar's brightness carefully over weeks or months, catching the flickering of the accretion disk and the delayed response in the emission lines. For an object as distant as TON 618, this is very difficult. The quasar is faint, it requires large telescopes and long observing campaigns, and the cosmic time dilation introduced by its high redshift stretches out the variability timescales, making the monitoring even more demanding. In practice, for many quasars, including TON 618, astronomers use a shortcut. Instead of conducting a full reverberation mapping campaign for each individual quasar, they use relationships established from quasars that have been mapped. Decades of reverberation mapping have shown that there is a consistent correlation between the luminosity of a quasar and the size of its broadline region. Brighter quasars have larger broadline regions, and the relationship follows a predictable pattern. By measuring the luminosity of a quasar, which is relatively straightforward, astronomers can estimate the size of its broadline region using this calibrated relationship. Then they combine that estimated distance with the measured line width to calculate the mass. This is sometimes called the single epoch method because it requires only a single spectrum of the quasar, not months of monitoring. It's efficient and widely used. But it introduces additional uncertainty because you're relying on a statistical relationship rather than a direct measurement of the time lag. The scatter in the luminosity size relationship is real. Individual quasars can deviate from the average relationship by a factor of 2 or 3. This means the mass estimates for any single quasar, including TON 618, carry uncertainties that are typically quoted as a factor of a few. The true mass could be half the estimated value, or it could be twice the estimated value. When astronomers say the mass of TON 618's black hole is about 66 billion solar masses, what they mean more precisely is that it falls in a range that likely spans from perhaps 30 billion to well over 100 billion solar masses, with 66 billion being the best estimate from the available data. That uncertainty is important. It's honest. And it matters enormously when people try to rank black holes and declare one the biggest. There's also a second, independent way to constrain the mass, and we touched on it earlier, the Eddington luminosity. This is the theoretical maximum brightness an accreting object can sustain. Beyond this limit, radiation pressure overwhelms gravity and blows away the infalling material, choking off the fuel supply. The Eddington luminosity depends directly on the mass of the black hole. A more massive black hole has stronger gravity, so it can hold onto material against more intense radiation pressure, supporting a higher luminosity. By measuring the observed luminosity of TON 618 and comparing it to the Eddington limit, astronomers can estimate a minimum mass for the black hole. If the quasar is radiating at or below the Eddington limit, which is the physically expected situation, then the mass must be at least large enough for the Eddington limit to equal or exceed the observed luminosity. If the mass were too small, the Eddington limit would be lower than what's observed, which would mean the quasar is somehow exceeding its theoretical maximum. That's not impossible. There are scenarios involving super Eddington accretion, but for a first estimate, it provides a useful lower bound. For TON 618, the Eddington argument confirms that the black hole must be in the range of tens of billions of solar masses. The two methods, virial estimation from emission lines and Eddington constraint from luminosity, point to the same general answer. They agree. And when two independent methods agree, the conclusion becomes more robust, even if neither method alone is perfectly precise. But this is where we need to be careful about certainty. Because there are other extremely massive black hole candidates in the universe, and some of them may rival or even exceed TON 618's estimated mass. Phoenix A is a supermassive black hole at the center of a galaxy in the Phoenix Galaxy cluster, roughly 5.8 billion light years from Earth. Its mass has been estimated at roughly 100 billion solar masses. If that estimate holds, Phoenix A would be significantly more massive than TON 618. But the Phoenix A estimate was made using a different technique, one based on the relationship between a black hole's mass and the velocity dispersion of stars in the host galaxy's central bulge. This method works well for nearby galaxies where the stellar motions can be resolved, but for distant galaxies, it relies on extrapolating calibrated relationships and is subject to its own set of uncertainties. Holm 15, I star, at the center of the galaxy. Holm 15A in the Able 85 galaxy cluster has an estimated mass of roughly 40 billion solar masses. This estimate was derived from stellar dynamical modeling, fitting the observed motions of stars to determine how much mass must be concentrated at the center. It's considered one of the more robust measurements among ultramassive black holes because it relies on directly observed stellar kinematics rather than quasar emission properties. But even here, assumptions about the galaxy's structure and the distribution of dark matter introduce uncertainty. NGC 4889, a giant elliptical galaxy in the Coma cluster, has a black hole with a mass estimated between roughly 6 billion and 21 billion solar masses. The range is that wide because different studies using different methods and datasets have produced significantly different results. This example illustrates how even supposedly well-studied objects can have mass estimates that vary by factors of 3 or more depending on methodology. NGC 1277, a compact galaxy about 220 million light-years away, was once claimed to host a black hole of roughly 17 billion solar masses, an extreme value for a galaxy of its size. Later studies revised the estimate significantly downward. The discrepancy came from different assumptions about the galaxy's stellar population and the modeling of its dynamics. What initially looked like a record-breaking measurement became a cautionary tale about the difficulty of black hole mass estimation. The lesson from all these examples is consistent. Black hole mass estimates for distant objects are inherently uncertain. They depend on the method used, the quality and type of data available, the assumptions embedded in the analysis, and sometimes on which research team perform the work. Two equally competent groups can analyze the same object and get different answers. Not because one is wrong, but because they made different but equally reasonable assumptions about parameters that aren't directly measured. This is why it's misleading to declare any single black hole as definitively the most massive in the universe. TON 618 is certainly one of the most extreme black hole mass candidates ever identified. It sits firmly in the category of ultramassive black holes, those exceeding 10 billion solar masses. But whether it is the largest, or whether Phoenix A or some yet undiscovered object holds that distinction, is not something current data can resolve with certainty. What we can say confidently is that TON 618 belongs to an extraordinarily rare class of objects. The number of black holes reliably estimated to exceed 10 billion solar masses is very small, probably countable on two hands. These are extreme outliers in the population of supermassive black holes, the very far tail of the mass distribution. It's also worth noting what future observations might change. The next generation of extremely large telescopes currently under construction will have mirrors 30 to 40 meters in diameter, vastly exceeding anything currently available on the ground. These instruments will be able to resolve finer detail in the spectra of distant quasars, improving the precision of emission line measurements. They may also enable reverberation mapping campaigns for quasars that are currently too faint for this technique, replacing the statistical single epoch estimates with direct time lag measurements. Space-based observatories operating at X-ray and ultraviolet wavelengths will complement these ground-based observations, probing the inner regions of accretion disks where the most extreme physics plays out. Better data will produce tighter constraints. Some mass estimates may go up, others may come down. The ranking of the most massive black holes could shift. What is unlikely to change is the fundamental conclusion that black holes in the tens of billions of solar masses range exist. The specific number for TON 618 may be revised, but the object will remain in the ultramassive category regardless. There's another subtlety that deserves mention. Everything we observe about TON 618 is filtered through more than 10 billion light years of intervening space. The light has traveled across a significant fraction of the observable universe to reach our telescopes. During that journey, the expansion of the universe has stretched the light's wavelength by a factor related to the redshift. At a redshift of 2.22, the light we observe today was emitted at wavelengths roughly 3 times shorter than what we actually detect. An emission line that was originally in the ultraviolet has been shifted into the visible or even near infrared part of the spectrum by the time it reaches Earth. This means that the emission lines astronomers use to estimate the black hole's mass are not always the same lines they would use for a nearby object. For quasars at lower redshifts, astronomers often rely on the hydrogen beta emission line, known as H beta, which is well calibrated and well studied. But for high redshift quasars like TON 618, H beta is shifted out of the easily observable range. Instead, astronomers must use different lines, such as the magnesium 2 line or the carbon 4 line, which are emitted at shorter wavelengths and thus shifted into the observable window at high redshift. These different emission lines come from gas at different distances from the black hole and respond differently to the quasar's radiation. Calibrating these lines against H beta, ensuring that they give consistent mass estimates, is an ongoing area of research. Cross-calibration between different lines introduces its own uncertainties. 2 different lines measured in the same quasar can sometimes give mass estimates that differ by a factor of 2. This is another reason why the mass of any high redshift quasar's black hole should be treated as an estimate, not a precise measurement. None of this invalidates the measurement. It contextualizes it. Science is honest about its limitations, and understanding those limitations is what separates a well-grounded estimate from a guess. The mass of the black hole in TON 618 is not a guess. It's an estimate derived from multiple converging lines of evidence using methods that have been tested and validated against independent measurements in nearby galaxies. The physics underlying these methods is well understood. The uncertainties are real but bounded. The number could be somewhat different from 66 billion solar masses, but the basic conclusion that this is one of the most massive black holes ever measured rests on solid ground. And it is precisely this conclusion that creates the deepest and most fascinating problem. Because the existence of a black hole this massive, observed at a time when the universe was only about 3 billion years old, poses a serious challenge to our understanding of how black holes grow. There are physical limits to how fast a black hole can gain mass, limits rooted in the same accretion physics we've been discussing. And when you run the numbers, when you start with a plausible seed and let it grow at the maximum possible rate, reaching 66 billion solar masses in 3 billion years is extraordinarily difficult. The growth required is so extreme that simple models cannot account for it. This is the puzzle at the heart of the title. Not that black holes this massive are impossible. Clearly they exist because we observe them, but that they shouldn't be this massive this early. According to our most straightforward expectations about how black hole growth works, something unusual had to happen. Some pathway, some mechanism, some set of conditions that our simple models don't predict had to be at work to build an object this extreme in the time available. Understanding what those mechanisms might be and what they tell us about the early universe is where we turn next. We've now arrived at the heart of the puzzle. The question that makes TON 618 not just impressive, but genuinely troubling for astrophysics. We know this black hole has an estimated mass of 66 billion solar masses. We know it is observed at a redshift of roughly 2.22, meaning we see it as it existed when the universe was approximately 3 billion years old. We've established how astronomers measure its mass and what uncertainties accompany those measurements. But none of that addresses the deepest question. How did this black hole get so massive? And why is that question so difficult to answer? Because here is the problem. Black holes don't just appear at 66 billion solar masses. They have to grow. They start as something smaller and accumulate mass over time. And the universe imposes real physical limits on how quickly that growth can happen. When you take those limits seriously and work through the arithmetic, you find that building a black hole as massive as the one in TON 618 in the time that was available is extraordinarily hard to explain with straightforward growth. Not impossible, not forbidden by physics, but hard enough that simple expectations completely fail. Something unusual had to happen. And figuring out what that something was remains one of the great open questions in astrophysics. To understand why this is so hard, it helps to picture the universe as it actually existed during the epoch when TON 618's black hole was assembling its mass. We observe this quasar at a redshift of 2.22 when the cosmos was roughly 3 billion years old. But the growth had to begin much earlier than that. The seed, whatever it was, probably formed within the first few 100 million years after the Big Bang. So we need to understand what the universe looked like during that critical window, from roughly 100 million to 3 billion years after the beginning. The early universe was profoundly different from the cosmos we inhabit today. In the first few 100 million years, no stars had yet formed. The universe was filled with a nearly uniform fog of hydrogen and helium gas, slowly cooling as the cosmos expanded. There were no heavy elements, no carbon, no oxygen, no iron. Those elements are forged inside stars, and no stars had yet lived and died to create them. Gravity was already at work, pulling slightly denser patches of gas together, the seeds of what would eventually become galaxies. But the structures were embryonic. Not galaxies as we would recognize them, but dark matter halos, invisible gravitational scaffolding where gas could accumulate and eventually ignite into the first stars. Those first stars, known as population 3 stars, were unlike anything in the modern universe, formed from pristine hydrogen and helium with no metals to cool the gas efficiently. They were probably enormous. Theoretical models suggest they could have reached masses of several hundred solar masses, possibly even 1,000. They burned hot and bright and died fast, some within just a few million years. Many of them would have ended their lives in cataclysmic explosions, enriching the surrounding gas with heavy elements for the first time. Others, the very most massive, may have collapsed directly into black holes without an explosion at all. their cores falling inward so completely that no supernova blast could escape. By about 300 to 500 million years after the Big Bang, the first small galaxies were forming. These weren't the grand spirals and ellipticals we see today. They were irregular clumps of gas and young stars, perhaps a few thousand light years across, each containing maybe a billion solar masses of material, or less. But they were everywhere. The universe at this epoch was denser than it is today. Galaxies were closer together, collisions and mergers were frequent, far more common than in the modern universe where expansion has pushed galaxies apart. This dense, chaotic environment provided both the raw material and the delivery mechanism for rapid black hole growth. Gas was abundant, mergers were constant, fuel was being funneled toward galactic centers by gravitational interactions on a regular basis. By the time the universe was 1 to 2 billion years old, genuine galaxies were assembling rapidly. Some of these early galaxies were already massive, containing tens of billions of solar masses of stars and gas. The most overdense regions of the cosmos, the places where the initial density fluctuations from the Big Bang were slightly larger than average, were the first to form large structures. These regions became the ancestors of what we see today as galaxy clusters, the densest knots in the cosmic web. And it was probably in these overdense environments that the most extreme black holes got their start. More gas, more mergers, more fuel, more opportunities for rapid growth. This is the environment in which the black hole powering TON 618 had to grow from a seed to 66 billion solar masses. A universe that was young, dense, gas-rich, and violent. A universe where the conditions for extreme growth were more favorable than they would ever be again. Let's start with the basics of growth. How do black holes grow? There are two primary mechanisms. The first is accretion, the process of consuming surrounding gas, dust, and other material. This is the same process that powers quasars. Material falls toward the black hole, forms an accretion disk, heats up, radiates energy, and eventually crosses the event horizon, adding its mass to the black hole. Accretion is the dominant growth mechanism for most of cosmic history. Wherever there is gas available near a black hole, accretion can occur. The second mechanism is mergers. When two galaxies collide, their central black holes can eventually spiral toward each other, driven by gravitational friction with surrounding stars and gas, and merge into a single, more massive black hole. Each merger can potentially double or more than double the mass in a single event. Both mechanisms contribute to the growth of supermassive black holes, and both face their own limitations. Let's focus on accretion first because it is both the primary growth channel and the one with the most clearly defined speed limit. When a black hole accretes matter, something counterintuitive happens. We discussed the Eddington limit earlier in the context of luminosity, the balance point where outward radiation pressure from the accretion disk exactly matches the inward pull of gravity. But that same limit has a second consequence that matters enormously here. It doesn't just cap how brightly a black hole can shine, it caps how fast a black hole can grow. Because the maximum rate at which material can fall in is set by the same balance. If you try to feed the black hole faster, the radiation blows the fuel away. The Eddington limit, named after the British astrophysicist Arthur Eddington, is simultaneously a luminosity ceiling and a growth rate speed limit. The key parameter is the EE folding time, the time it takes for the black hole to grow its mass by a factor of roughly 2.7 if it's accreting continuously at the maximum Eddington rate. For standard assumptions about how efficiently infalling matter is converted into radiation, typically around 10% efficiency, the EE folding time works out to approximately 45 million years. In practical terms, this means a black hole feeding at maximum rate roughly doubles its mass every 30 million years or so. That sounds fast, but the consequences of exponential growth are deceptive. Doubling sounds modest, but to go from a small seed to 66 billion solar masses, you need many, many doublings. Let's walk through the arithmetic in plain terms. Suppose you start with a stellar mass black hole, the kind left behind by the death of a massive star. A typical seed mass might be around 10 to 100 solar masses. Let's be generous and start with 100 solar masses. To reach 66 billion solar masses from 100 solar masses, you need to multiply the mass by 660 million. How many doublings does that take? Each doubling multiplies the mass by 2. You need roughly 29 to 30 doublings to reach a factor of 660 million. At 30 million years per doubling, 30 doublings takes about 900 million years. Call it roughly 1 billion years. On the surface, that seems comfortably manageable. The universe was about 3 billion years old when we observed TON 618. So if the seed formed very early, say within the first few 100 million years after the Big Bang, there would appear to be more than enough cosmic time for roughly 1 billion years of continuous Eddington rate accretion. The math appears to work with room to spare. But appearances are deeply misleading here, because this calculation assumes perfection. It assumes the black hole was accreting at the absolute maximum possible rate, without interruption, for over 1 billion years straight. In reality, accretion is messy. Black holes do not feed continuously. The supply of gas near a black hole is not constant. Gas has to be funneled from the surrounding galaxy into the central region, which requires specific conditions. Gravitational interactions, galaxy mergers, gas cooling, and angular momentum transport all play roles, and none of these processes operate with perfect efficiency or perfect timing. There are periods when the gas supply is abundant and the black hole feeds voraciously. And there are periods, potentially long ones, when the supply dries up and the black hole sits dormant, gaining no mass at all. Even when gas is available, maintaining accretion at the Eddington limit is extremely difficult. The radiation produced by the accretion disk doesn't just push against infalling material, it can also heat the surrounding gas, causing it to expand and become less dense, making it harder for gravity to pull it inward. Powerful jets and outflows launched by the accretion process can blow gas completely out of the black hole's vicinity, clearing out the fuel supply for millions of years. This is called feedback, and it is one of the most important processes in galaxy evolution. The very act of a black hole feeding creates conditions that tend to shut off future feeding. So the real duty cycle, the fraction of time a black hole actually spends accreting at or near the Eddington rate, is likely well below 100%. Estimates vary, but many models suggest duty cycles of 10 to 30% for the most active phases. If a black hole only accretes at the Eddington rate 30% of the time, the effective doubling time stretches from 30 million years to 100 million years. 30 doublings at 100 million years each would take 3 billion years. And the seed didn't form at the instant of the Big Bang. It formed at least 1 or 200 million years later. The universe was only about 3 billion years old when we observed TON 618, and the seed needed at least a couple 100 million of those years just to form. There simply isn't enough time. This is the core of the problem. Under realistic assumptions about accretion, starting from a stellar mass seed, you cannot build a 66 billion solar mass black hole by the time the universe is 3 billion years old. The Eddington limit, combined with realistic duty cycles and feedback, simply does not allow it. The growth is too slow and the time is too short. And the problem gets worse if you consider the very earliest phases. The first stars in the universe, population 3 stars, likely formed around 100 to 250 million years after the Big Bang. These were probably very massive stars, perhaps hundreds of times the mass of our Sun, and they would have left behind black holes of roughly 100 to several hundred solar masses when they died. But even if those seeds formed at the very earliest possible moment, they still need over 1 billion years of near continuous Eddington accretion to reach the masses we observe in the most extreme quasars. And the early universe, while rich in gas, was also chaotic and turbulent. Conditions that don't necessarily favor steady, efficient accretion. So astronomers have been forced to consider alternatives, ways to cheat the simple growth calculation, ways to get a head start, or to break the speed limit, or to take shortcuts that the straightforward model doesn't allow. The first major alternative is the idea of heavy seeds. Instead of starting with a stellar mass black hole of 100 solar masses and trying to grow it up through accretion, what if you could start with something much more massive? What if the seed itself were already 10,000 or 50,000 or even 100,000 solar masses? If you start with a heavier seed, you need fewer doublings to reach the final mass. Starting from 100,000 solar masses instead of 100, you eliminate roughly 10 doublings from the calculation. That saves roughly 300 million to 1 billion years, depending on your assumed duty cycle. It dramatically relaxes the time constraint. But how do you form a seed that massive without going through the normal stellar evolution pathway? The answer may lie in a process called direct collapse. In the early universe, under very specific conditions, a massive cloud of primordial gas, primarily hydrogen, could have collapsed directly into a black hole without first forming a star. The key requirement is that the gas must not fragment into smaller clumps. In normal star formation, gas clouds cool by radiating energy, which causes them to fragment into many smaller pieces that each form individual stars. But if something prevents this cooling, if the gas stays hot and doesn't fragment, then the entire cloud can collapse as one single object, forming a massive black hole directly. What could prevent the cooling? One possibility is intense ultraviolet radiation from nearby star-forming regions. This radiation can destroy the molecular hydrogen that normally allows gas to cool efficiently. Without that cooling channel, the gas stays hot, doesn't fragment, and collapses monolithically. The result is a so-called direct collapse black hole, potentially born with a mass of 10,000 to 100,000 solar masses or more. These objects have never been directly observed. They are theoretical predictions. But simulations show that the conditions for their formation could have existed in the early universe, particularly in dense environments near the first galaxies. If direct collapse black holes did form, they would provide exactly the kind of heavy seed needed to explain how the most massive black holes grew so large so quickly. The second alternative is super Eddington accretion. The Eddington limit is calculated assuming that radiation is emitted uniformly in all directions. But real accretion disks are not perfectly symmetric. They're flattened structures, and in some configurations, radiation can escape preferentially along certain directions, particularly along the poles of the disk, while material continues to fall in along the equatorial plane. In these situations, the effective accretion rate can exceed the Eddington limit because the infalling material is partially shielded from the outgoing radiation. Some theoretical models and simulations suggest that black holes in the early universe, surrounded by dense, rapidly infalling gas, could have accreted at rates several times or even tens of times above the classical Eddington limit for sustained periods. This so-called super Eddington or hyperaccretion phase would dramatically accelerate growth. Instead of doubling every 30 million years, the black hole might double every few million years during these extreme episodes. Even brief periods of super Eddington accretion, lasting tens of millions of years, could add enormous amounts of mass, effectively compressing what would normally take hundreds of millions of years of growth into a much shorter interval. There is circumstantial evidence that super Eddington accretion occurs. Some quasars and active galaxies appear to be radiating above their calculated Eddington limits, suggesting their black holes are consuming material faster than the classical theory would allow. Narrow-lined Seyfert 1 galaxies, for example, often show signs of accretion rates exceeding the standard limit. And simulations of early universe conditions consistently produce episodes of super Eddington infall when large quantities of gas are funneled toward a central black hole during galaxy formation or mergers. But super Eddington accretion is not a permanent solution. It requires enormous gas supplies in the immediate vicinity of the black hole. Those supplies get consumed or blown away. The episodes are likely intermittent, not continuous. So while super Eddington accretion can boost the growth rate during favorable periods, it probably cannot sustain that boosted rate for billions of years. It's a temporary accelerant, not a permanent engine. The third mechanism is mergers. When galaxies collide, and they collided frequently in the early universe when galaxies were closer together and the cosmos was denser, the supermassive black holes at their centers can eventually merge. Each merger can significantly increase the mass of the resulting black hole. If two black holes of comparable mass merge, the product is roughly twice as massive as either parent. In principle, a series of major mergers could rapidly build mass without relying on accretion at all. But mergers have their own problems. First, getting two supermassive black holes to actually merge takes time. When two galaxies collide, their black holes don't immediately fall together. They settle toward the center of the merged galaxy through a process called dynamical friction, where gravitational interactions with surrounding stars gradually drain their orbital energy. This process can take hundreds of millions of years. Once the two black holes are close enough, they form a bound pair, a binary, and begin orbiting each other. But shedding enough energy to spiral inward and finally merge can take even longer, potentially billions of years in some models. This is known as the final parsec problem, the difficulty of getting two supermassive black holes from a separation of a few light years down to the point where gravitational wave emission takes over and drives them together. The total time from galaxy collision to black hole merger can be comparable to the entire age of the early universe. Second, mergers don't create mass from nothing. They combine existing mass. For mergers to contribute significantly to building something like TON 618, the merging black holes must themselves already be massive. And that brings us back to the original question: how did those precursor black holes get massive in the first place? Mergers can redistribute and combine mass, but the mass had to be accumulated somehow. Ultimately, accretion must have played a role in building up the individual black holes before they merged. The most likely explanation for objects like TON 618 is that all three mechanisms played a role. The story probably goes something like this. In the early universe, within the first few 100 million years after the Big Bang, conditions in certain dense regions allowed the formation of heavy seed black holes, either through direct collapse of massive gas clouds or through the rapid growth of the remnants of the very first massive stars. These seeds, perhaps tens of thousands of solar masses, then grew rapidly through accretion, fueled by the abundant gas available in the young, dense cosmos. During favorable periods, accretion may have proceeded at super Eddington rates, temporarily exceeding the classical speed limit. Simultaneously, the host galaxies were growing through mergers with other galaxies. Each major merger brought in additional gas to fuel accretion and potentially delivered additional black holes that eventually merged with the central one, adding their mass in a single event. Over the course of roughly 2 to 3 billion years, this combination of a heavy initial seed, periods of extremely rapid accretion, and successive mergers built the black hole to the extraordinary mass we observe today. No single mechanism was sufficient on its own, but together, in a rare convergence of favorable conditions, they could produce an object of 66 billion solar masses within the available cosmic time. And this is the critical nuance of the phrase, shouldn't get this big. It does not mean that the laws of physics forbid it. Clearly they don't, because the object exists. It means that the simplest, most straightforward model of black hole growth, start with a small seed, accrete at the Eddington rate, and grow steadily, cannot produce this result. To explain TON 618, you need to invoke special conditions: heavy seeds, super Eddington episodes, favorable merger histories, a rare combination of circumstances that most black holes in most galaxies never experienced. That is why objects like TON 618 are so rare. Not because they're impossible, but because the path to creating them is narrow. Most black holes start smaller, grow more slowly, experience more interruptions, and end up far less massive. The black hole in the center of our own Milky Way, Sagittarius E star, at 4 million solar masses, probably grew mostly through modest accretion over billions of years, never coming close to the extreme conditions required to reach the masses we see in the most luminous quasars. TON 618 represents the far, far end of the tail, the rare outcome. The black hole that grew under nearly ideal conditions for nearly the maximum possible duration, through nearly every available growth channel, and still barely fits within the constraints of cosmic time. It is an outlier in the most extreme sense, and that is precisely what makes it so valuable to science. Outliers test theories. Objects at the extreme edges of what should be possible force models to confront their weaknesses. If our models of black hole growth couldn't produce anything like TON 618 under any reasonable conditions, that would mean our understanding of accretion physics, or seed formation, or merger dynamics, or the conditions of the early universe was fundamentally wrong somewhere. The fact that we can construct plausible pathways, pathways involving heavy seeds and super Eddington accretion and mergers, means our understanding is at least on the right track. But the narrowness of those pathways, the specific conditions required, tells us that there is still much we don't understand about the earliest phases of black hole growth and the environments in which the most massive black holes formed. The James Webb Space Telescope is already finding surprises in this area, and the discoveries are sharpening the puzzle in real time. Since its first science observations began in 2022, the telescope has peered deeper into the early universe than any instrument before it, detecting galaxies and active black holes at redshifts that push well beyond 10, corresponding to a time when the universe was less than 500 million years old. One of the most striking discoveries is an object called UHZ1, detected behind the galaxy cluster Abell 2744, which acts as a gravitational lens magnifying the distant source. UHZ1 appears to host an active black hole with a mass of roughly 10 million to 100 million solar masses, and it exists at a redshift of roughly 10.1, meaning we see it when the universe was only about 460 million years old. A black hole of tens of millions of solar masses, when the cosmos was less than 500 million years old, is extremely difficult to build from a stellar mass seed, even with continuous Eddington accretion. The existence of such an object strongly suggests that heavy seeds, possibly direct collapse black holes, played a role. Then there is Sears 1019, a galaxy at a redshift of roughly 8.7, observed when the universe was about 570 million years old. This object hosts an actively accreting black hole estimated at roughly 10 million solar masses. What makes Sears 1019 particularly interesting is that the black hole appears to be small relative to its host galaxy, the opposite of what simple models predict for rapidly growing early black holes. This suggests the growth histories of early black holes and their galaxies are more complex and varied than previously assumed. Beyond individual objects, the James Webb Space Telescope has revealed that luminous galaxies in general seem to be more common in the early universe than expected. Some of these galaxies are surprisingly massive, containing tens of billions of solar masses of stars at redshifts of 9, 10, and beyond. If galaxies could assemble that much stellar mass that quickly, the conditions were clearly favorable for rapid growth of all kinds, including the growth of central black holes. The dense, gas-rich environments that built those early galaxies may have been the same environments that fueled the most extreme episodes of black hole accretion. These discoveries do not solve the puzzle of TON 618, but they sharpen it. They tell us that the early universe was even more efficient at building massive structures than our models predicted. And if the universe could build massive galaxies that quickly, the idea that it could also build ultra-massive black holes, given the right combination of heavy seeds, rapid accretion, and frequent mergers, becomes more plausible. There's also a statistical argument worth considering. TON 618 is one object. We observe it because it happens to be extraordinarily luminous and happened to fall within the survey region of a mid-20th century photographic plate. But the observable universe is vast. It contains roughly 2 trillion galaxies. If even a tiny fraction of those galaxies hosted black holes that grew under similarly extreme conditions, the total number of ultramassive black holes in the observable universe could be in the thousands or tens of thousands. We don't see most of them because they may no longer be active. A quasar shines only while the black hole is feeding. Once the gas supply is exhausted, the quasar dims and the black hole becomes invisible. A dark engine sitting silently at the center of its galaxy. There could be enormous numbers of dormant, ultramassive black holes scattered throughout the cosmos, relics of extreme growth episodes that ended billions of years ago. We would have no easy way to detect them unless they happen to be in galaxies close enough for us to measure stellar dynamics near the center. This means TON 618 may not be as exceptional as it appears. It may simply be one of the few ultra-massive black holes we've caught in the act of feeding. The others have gone dark. If that's true, then the pathways to extreme mass, heavy seeds, super Eddington accretion, frequent mergers may have been more common in the early universe than we currently estimate. The puzzle isn't just how one black hole got this big, it's how many did, and what that tells us about the conditions that prevailed in the first few billion years of cosmic history. This is a living, active area of research. The answers are not settled, and that is what makes it exciting. So, what does TON 618 ultimately teach us? It teaches us that the universe is capable of building objects of almost incomprehensible mass in surprisingly short periods of time. It teaches us that simple expectations about how things grow can break down in the real universe, where conditions vary enormously from one environment to another. It teaches us that the most extreme objects are the most informative, because they mark the boundaries of what is possible and force us to refine our understanding. When you look at TON 618, you are not just looking at a bright dot more than 10 billion light years away. You are looking at one of the most massive single objects in the observable universe. A black hole with an event horizon larger than our entire solar system. An engine of destruction that outshines whole galaxies. And a profound puzzle that challenges everything we thought we understood about how quickly the cosmos can assemble its most extreme creations. The black hole at the center of TON 618 was not supposed to get this big. Not because the laws of physics prevent it, but because every straightforward path to building it falls short. And yet there it is, shining across 10 billion light years of space. A testament to the fact that the universe does not always follow the simple path. Sometimes it finds extraordinary ways to build extraordinary things. That point of light you'd see through a telescope, faint and unremarkable to the untrained eye, is actually one of the most extreme objects we have ever discovered. Behind it lies a story that spans the full history of the cosmos. From the first clouds of hydrogen collapsing in the dark to the monstrous engine radiating across the observable universe today, and we, standing on a small rocky planet, orbiting an ordinary star in a quiet arm of an ordinary galaxy, have figured out how to read that story from nothing more than the light that reaches our telescopes. The universe built TON 618 in defiance of simple expectations. And we, against all odds, understood what it built. That is the true scale of this discovery. Not just the mass, not just the size, not just the luminosity, but the depth of the question it poses and the reach of the minds that wrestle with it. A single point of light, more than 10 billion light years away, and the slow, careful, brilliant work of human beings, turning photons into understanding. The next time someone tells you that black holes are just objects where nothing escapes, remember TON 618. Remember that somewhere in the distant universe, there exists a single gravitational engine more massive than the combined stellar population of our entire galaxy. Remember that its event horizon dwarfs the solar system. Remember that its light has been traveling towards us for longer than the Earth has existed. And remember that we found it, measured it, and asked the hardest question of all: how? We don't have the final answer yet, but we're closer than we've ever been. And the search itself, that patient, relentless effort to understand the most extreme things the universe can create, is one of the most extraordinary things humanity has ever undertaken.